All right, welcome back to my YouTube channel again today. So today we talk about the forced damped harmonic oscillator. I'm going to derive a steady-state solution, the resonance frequency, and also the mechanical impedance of this system. So first of all, we're going to answer this few questions by watching this animation. So what happens when an oscillating system is continuously forced by an external periodic force? Also, what happens when the driving force approaches the natural frequency of the system? So this is a driven oscillation, and we're going to answer these two questions as we derive all our parameters. So let's dive in deeply into the context for today. So first of all, we're going to know what is a driven oscillation, and this is a short note on the driven oscillation. So a driven oscillation is an oscillatory motion of a system subjected to a continuous external periodic force. And a periodic force is given by this expression. You see, now a periodic force is a function of time. So this expression here, or this sentence here, answers our first question that says, when the natural frequency of the oscillator is not the same as the frequency of the impressed force. The natural frequency of the oscillator force dies out soon and begins to oscillate with the frequency of the impressed periodic force. So the vibrations which are maintained are called the forced vibrations. So if we recall, for a damped oscillator, mx double dot plus bx dot plus kx is equal to 0. So this is for a damped oscillator, so we call it DHM, a damped harmonic motion. So for a forced harmonic motion, we no longer have 0, but we have periodic force pasted there. So if we divide through by m in this equation, we are going to finally have this again. So we have here that capital letter F naught is small f naught over m for equation 3. Now you notice that equation 3 is a non-homogeneous second order differential equation, and the solution to this equation is going to be gotten by first of all finding the complementary function and also finding the particular integral. So to find the complementary function of equation 3, we first of all have to solve the equation when x double dot plus gamma x dot plus omega naught square x is equal to 0. So solve this equation, it gives us our complementary function. Then when we replace the periodic force, it gives us our we can now solve for our particular integral. So let's go into the complementary function. So before we do that, we can express equation 3 in terms of exponential function by saying this, and we can work with the positive. Let's remove this negative from here. So let's work with positive. So our complementary function will be gotten as we have done before in damped harmonic motion. So this is going to be our complementary function. We have done this solution before. First of all, solving the auxiliary equation of x double dot plus gamma x dot plus omega naught square x equal to 0. The auxiliary equation is going to be m square plus gamma m plus m square, please, plus gamma m plus omega naught square equal to 0. So that's our auxiliary equation, of which the solution is this. So this is the solution for the complementary function. So we can now look for the particular integral. And before we do that, you must note that this is the transient solution. Why? Because as time extends to infinity, this will become 0. This entire expression will blow up to 0. So this is the transient solution of the differential equation. So to obtain the steady state solution, you must first find the particular integral. And we can do that by, let's apply a little mathematics here. Now, if you consider a second order non-homogeneous differential equation of the form a d square x over dt square plus b dx over dt plus cx equal to e to the power of at, then the particular integral is gotten by doing this. So this is going to be the solution for the particular integral. V of t is equals to 1 over f of d e to the power of at, which is equal to 1 all over f of a e to the power of at. So if we have f of a to be equal to 0, then it means that we are going to differentiate. So it means the particular integral is going to be this. And similarly, if f prime of a is t equal to 0, then the particular integral v of t should now become 1 over f double prime of a times e to the power of at times t square. So that's what it's going to be. So if f double prime is t0, we continue again. So let's move on for this particular expression. So it means from equation 6, this is our equation we are about to solve. Don't forget we are concerned about this part. So it means that the particular integral will become this f of d. It means in place of our derivative here, we replace it with d. So it means x double dot will become d square, x dot will become ordinary d. That is the meaning. So if you do that, you're going to have 1 over d square plus gamma d plus omega naught square. Now we said f of d will be replaced by f of a from here. F of d is replaced by f of a. So it means in place of d, we are going to replace by a. So now in place of d in this solving, we are going to replace by I omega. So if we replace that here, we are going to finally have this expression. And of course, it's not equal to 0. So that is our particular integral. So the general solution will become the solution, the addition of the complementary function u plus our particular integral v. So if we add both together, this becomes our general solution for this equation. So move on. So we can still evaluate the particular integral further by doing this. Our aim is to find the steady state solution. So we can let the denominator just now to be equal to rho e to the power of I times phi. So we are converting it to polar form. So you know that this is a Cartesian form. So if we convert it to polar form, we have this. And if you remember, when z is equal to a plus ib, then it's equal to rho e to the power of I theta. Rho is going to be square root of a square plus b square. So this is what is going to be our r in this case. So our capital letter r in this case is now going to be square root of this. So this is everything here is like our a, and I omega gamma omega is like our b. So tan phi, you know, from here, tan phi is going to be b over a. So it's going to be b over a. So that's what we have. So we are going to have this, and if we replace it back, we're going to have v of t is equal to 1 over rho e to the power of I phi times this. And of course, we can just factorize. We can just factorize this, and it gives us this. We can just factorize this. So moving on, you could remember that by Euler's formula here, applied here, e to the power of I into bracket omega t minus phi should be equal to this. This is a mathematical expression that we are used to, where we have cosine of theta plus I sine of theta to be equal to e to the power of I theta. So that's the mathematical rule we use today. So v of t will be equal to this finally, where we are factorized and taking the real part. So it means that our x of t, our displacement is this is a transient solution and this is the steady state solution. So thus the steady state solution becomes, so it means if we do away with this this transient part where that becomes zero when time approaches infinity, we are left with this steady state solution, which is just this part of the equation. Now we can compress that and replace f naught over rho by a of omega. So if we do that, a of omega becomes our amplitude. So this expression here is our amplitude of the steady state solution. So let's do some analysis of the steady state solution. So at low frequency, this is what our amplitude is going to be. So at low frequency, the amplitude of the driven force is much less than the natural frequency of the system. And you'll notice that this can be absorbed since this is much more greater. So this can be absorbed away, leaving us with just omega naught raised to the power of 4. And of course, again, this can be absorbed inside because it's much smaller than omega naught to the power of 4. So if we absorb that, we end up having this as our final answer, and also this because this is absorbed into omega naught square. So again, at high frequency, omega is much greater than omega naught. And now what happens is that this will now be absorbed into omega square. So omega naught square should be absorbed into omega square. And if that is true, we are going to have this final expression as we see. Again, tan phi is going to be this, and if we absorb it again as we did before, that's still going to have this expression which is much less than 1. So in the resonance region, when omega approaches, as the driven force frequency approaches our natural frequency, then we have this expression. So we can either choose this or choose this. So if we subtract both together, we are going to have this final expression for our omega, our amplitude. So our resonance frequency. Now let's answer our second question, which says what happens when the driving force approaches the natural frequency of the system. When the frequency of the driving force omega approaches the natural frequency of the oscillator approaches resonance. And you must know that the resonance frequency is the specific frequency of an external driving force at which a mechanical system responds with maximum possible amplitude here. So let's see how we can derive that. So this is our amplitude of the system, the steady state solution. This is the amplitude of the system. Now we can get the maximum possible amplitude when we differentiate d of omega all over d of omega. If we differentiate this and equate it to 0, we'll get the maximum possible amplitude. So instead of differentiating the entire a of omega, we can just take the denominator and differentiate it instead of passing through all the plenty algebra, because we are still going to we're still going to divide 0 by that, and it's still going to give us 0. So we can just take only this expression and call it g of omega, and this is what we are going to differentiate at our driving force frequency approximately equal to our natural frequency here, as seen here. So if we differentiate this and equate it to 0, we are going to have this expression, and if we rearrange, we get this. So from here, if we make our omega subject, we're going to have this expression finally. So this is the expression for our resonance frequency, and we can still know that our quality factor is omega naught divided by gamma. So this expression here is the same as this expression. So we move further to the derivation of the mechanical impedance Zm of the forced oscillator. So let's see, for a mechanical oscillator, the mechanical impedance is the ratio of the force amplitude to the velocity amplitude. So this is mathematically given as this. So F naught over V, the force amplitude means this is our periodic force. F of t equal to F naught cosine of omega t. So this is our periodic force. So this becomes our force amplitude, F naught. And V as well as our velocity amplitude. It doesn't have the time part, just only the amplitude on it. So we can derive the mechanical impedance by first of all recalling our forced harmonic oscillator equation of motion. And the steady states, remember x, the displacement for our steady state, x of t is equal to a of omega cosine of omega t plus phi. So that is the displacement. So we can still write this as x equal to x naught e to the power of I omega t. So we can still do that. You can still write that expression out as the steady state solution of the displacement. So we can find x dot by differentiating. We can find x double dot again by differentiating again. And if we substitute it back into equation 13, we are going to have this expression. So we simply substitute it back into equation 13. And now we can do some mathematical manipulation here in this expression here. And we finally have this. So mind you, we've done some mathematical manipulation here again. And we have this. And finally, this is our magnitude of the mechanical impedance, which is square root of b squared plus m omega minus km all squared. So let's see this quick example on the damped harmonic motion, on forced harmonic motion, please. So this is a quick example. We are told that the equation of motion of a point mass is given as this. So we quickly know that this is a forced damped harmonic motion simply because of this steady state, this periodic force that was given here. So you can calculate. I'm going to only calculate the resonance frequency here. So you do the work by calculating the mechanical impedance and the impedance per unit mass. So our resonance frequency here, again, as we remembered, is given by this expression. So we can know that from mx double dot plus bx dot plus kx equal to f naught sine omega t. So by comparison, m is equal to 3, b is equal to 7, and k is equal to 10. Don't forget that gamma is equal to b over m, and omega naught square is equal to k over m. So that is the expression that I used, that I converted here into this. All right, see you next class for some further problems and solution as well. I hope you learned something.